Okay, welcome everyone. Welcome Shinonso من Wirigo and our host today Sabah Hasbi.
Okay, so we start?
Yeah, let's do it.
Okay, so today we are gonna solve together this LeetCode challenge. Construct binary tree from Preorder and Inorder Traversal. So the point of this LeetCode is to make a binary tree, to create it from scratch. And we are given two arrays, and a preorder and an inorder for this binary tree. So preorder is where you start from the left node and then the node itself, and then you start from the node itself, then the left node, then the right node, in the way you're recording it. And the inorder is where you start from the left node, then the node itself, then the right, right child, the left child, the node itself, and then the right child. And with these two arrays, we're supposed to construct and return the binary tree. So let's take this here. Keep it here while we look at the examples. So in this case, the preorder would be 3, 9, 20. So preorder starts with the node itself, goes to the left, and then goes to the right. And then the inorder starts with 9. So it starts with the left child, and then the root, and then the right child. So in this case, 9, 3, 20. In this case, again, 15 starts first because it's the left of the node. So it skips this one, goes to the left, then back to the node, then to the right. The output is the actual binary tree that we're going to make. And this array is made out of integers, right, which are the values of the nodes.
How do we
So
know which one we're gonna connect?
what do you mean?
So like they give us two different arrays, or they are the same? Oh, they are the same. Okay, so they are the same binary tree, just order different.
Exactly. So they're both a different order of the same tree. We're supposed to take these two and somehow find the pattern to make the actual tree. So we know that the preorder is guaranteed to be correct. The inorder is guaranteed to be correct. And we know that each node in the preorder appears in the preorder, and that the values are unique. So we do not have to worry about having like wrong data, basically. We can trust what they give us to be correct. Yeah. It would be easier to explain this with a like more complicated tree. So I will try add in more nodes. Yes. Let's just put 5, and then plus, I guess, 1.
Why one array is not enough?
Okay, let's take this. So in the inorder, we know that it starts with the node. Okay, so this is our node. And then what's next? These
9.
are the children. We do not know that 9, maybe it has 9, and then 20 is the child of 9. And then 15 is the child of 20, and 7 is the child of 15. You know, we do not know the order in which this tree, because this does not take the null thingies that
I see.
it's in here. Now in this case, we know that 3 is the node, the root node, 9, right? And this is the
Child.
left child that has 20, this is these are the two children of 3, and then we know that
First.
9 has kids
Two.
with null null, and then 20 have kids of 15 and 7. But this does not support this null. It skips over them. So we basically have no
No idea.
info on which is which, right? Now, the other one, we know that this is a left node of some sort because it starts with the left node. But other than this being the left and this potentially being the right, we have no idea what's in the middle, what order this is. This could be the actual node, and it could be like something like this 15, and then 3, and then 9, and here could be 20 and 7, and then this would still be 9, 3, 15, 27. So we don't technically know the order, but together we get enough information to actually make a judgment and a pattern that we can follow.
I see.
Okay, so we'll keep this to the side.
I'm sorry, I didn't get that. Please, can you come again?
Which part exactly? Which part did you not get exactly? The difference, or?
Maybe he didn't know. Okay, can you clear that?
Sorry.
Shinanso?
What the question is? Sorry, can you hear me?
Yes, I can
Yes.
hear you now.
Yeah, can you hear me?
Yes.
Hello. Like, I'm a little bit confused. Like, I'm getting confused on the question. Are we supposed to find the middle value? Is that what we're actually supposed to find?
We have two arrays, two just normal arrays, and then we're supposed to, from these two arrays, make up a binary tree. So we're making a binary tree
Okay.
node by node, connecting them to each other based on the order given to
Okay,
us.
okay, okay. Because like I was hearing you.
Yes.
Like, because I was hearing you say something like finding the middle value, so that got me confused a little bit.
I was just answering Monsef's question on why one of them is not enough to make the tree.
Okay, okay, all right.
I was
Thank you.
just explaining each one and then what it's lacking in terms of order.
So what you understand so far is like they want us to create a tree and they give us two array instead of one because one is not enough to like have full idea how this tree look like. So we have to deal with in order tree and pre-order.
Yes.
That's a mystery.
Yes. I will complete my very miniature tree. Well, you can think of a way we can do
Okay.
this.
So I notice. So the first one is pre-order, I believe. So it starts from 3, 9, 20. So pre-order starts from the root, and then so I can always know the first number is the root. The second two are the child, and then
We're not sure that the second two are the child.
in pre-order we're not sure.
We know that this is a root and these are children. This could be 3, and then this is 20 could be a child of 9. They could be like
Maybe it doesn't have right child. Too many hours in the PLD. We just start like 10 minutes or so. Kinda just starting. Today we're gonna do only one LeetCode because there's a lot of thing going on with like final project and another project in Alex. So I noticed 392. So we know that this is pre-order. So we know the first one is root. The others are like children. Now we know the first child gonna be the first one gonna be one of the child of the root. So this is 100% guarantee. So 9 is guaranteed to be the child of the root. But 20, I don't know if it is child of 9 or child of 3. So I need to go back to in order, I think, to make sure somehow. So in order, it always starts from the bottom of the tree, I think, right? Bottom of the tree from the left side.
Yes.
So in this case, it's gonna start from like 8, and then 1, and then I don't know, 8. Okay, how in order go? Does it go from 9, 3, 15?
So,
Until the roots and go down again.
so left and then this root, and you don't go to the right until you've cleared all the lefts of the right. So 9 is the left. You go to its root, and then you skip this one until you have all the lefts of it. So 15, and then 20, and then 7.
So like you always start from the left far down. So you go 9, 3, then you find 20, but you go from the left again, 15, 20, and then you go to 7 when there is nothing. Okay, I see. So 8, 1, 6, 8, 1, 6, and then 9, 4, 5, 2,
and then 3, and then 15, 27. I believe.
3, 15, 27. Yes, I think so.
Check again. Okay, I think that's okay. It's correct. So this, I believe, even if it looks more complicated, it is easier to see the pattern. Now, the hardest part about this one, that it's just for you to see how things work, like how you can take both of these and
Mix them in
know
one.
which one is the node and which are the left nodes, which are the right nodes. So there's a pattern here that we must find for us to actually make the tree. So what do we know so far? We know that the pre-order starts with the root, and the in-order has the right side on the right and the left side on the left of the root.
Wait, can you repeat that?
We know two things. That pre starts with the root, that this should be smaller, and that in has the right side or the left nodes on the left, like it's ordered left, root, right. Left nodes on the left and right nodes on the right. And the node or the root in the middle. So if we have no left nodes, then it's gonna start with the root. Actually, it would make more sense if we put it here. Okay. So the left nodes are on the left, the node is in the middle somewhere, and the right nodes are on the right. If we have no right nodes, then the root is gonna be on the end. If we have no left nodes, then the root is gonna be in the beginning. So the in order is ordered from left, middle, and right, and the preorder starts with the root. That's all we know so far. How can we take advantage of these two pieces of information?
Okay, wait, let me think it in. Also, if someone have question, please like open mic talk or like write in chat. Do not be shy. So in left node, on the left, root in the middle, right node on the right. Okay, so for in order, it's in the left side it have left node, and in the middle there is the root, and the right
Well,
node.
not the middle. It's
I mean,
not the middle of the array.
Between
In the
like
middle
somewhere, yeah. Okay.
Yeah.
And the pre starts with the root. Okay. I will like if you can, but it will not make sense. I thought maybe if we did like colors for the roots,
I'm not sure
or
we
like
can
each
color
level.
individual ones.
Maybe
No, I can.
maybe just with
I'll
the
split it. I
No.
will split it.
no with the just with the pen with the pen and put like underline or something.
Okay. So
Let's say level 1, the root is blue. Maybe I put blue. Okay, where is it in the N? It is there. Okay, and now 9 and 20 maybe. We
okay,
didn't.
we have this version so far. What do we understand from this?
We understand that the left side have a lot of nodes.
Yes, well, you're correct. We understand from this that we can split this into left nodes and right nodes
But how are we gonna know that is the root?
because it's the first element of this. I know that this
Oh
is the
yeah.
first element. So I can split my tree in the middle. We have this left and this right. Now I can do the same thing. I don't think I have enough colors for this, but then we can move on to the next one. We have 9. We have
Then I
9
split
here.
that one.
Yes, we
Left.
split. We know that these are the left nodes of 9. These are the right nodes of 9. And same thing for 20, right?
Wait.
I have
How are we gonna know 20? Because 20 is because 3 9 there is 1. After 9 there is 1. 20 is far away to the right.
Well, if you see, we have 2 here, and it's the same one just below 3, just below the node, the root node. It's the same element before this one, and it's the same element before the root in the in order. So if we find this node, right, the root, we can go to the one before it, we can look for it in the pre-order and go to the next one. And this would be the start of the left, I guess, the right side.
Okay, so because the 2 is the last node on the left side, which means the in pre-order the same node gonna be connected to the root, or like the other side of the root.
So it is the last one visited here before I go to 3.
So it's gonna be
Right?
connected to 20.
Yeah.
And then I
It's
understand.
the last element I visit before going to 20 in both of them. This is the last element in the right side. And we know that. It's the same here. See, that 9 is before 20 and before the root, that is 3.
Okay, I see the pattern, yes.
And then you keep looking for the root and
Again,
splitting
6.
that. Yeah.
6 is the last element. But
let's look at the left side first. So for the left side, we have 1. This is the root of this subtree, right? And this is just one element. So
we don't
that
know it is the root, right? Because it can be child.
it's the next element. So 3 is the root of the tree, 9 is the left root, and then 1 is its child, like this. So you keep going down. And then to
Okay.
5, where you skip to this, where you skip to this, right? And then to 20. So you keep going down the pre-order.
Okay, so
So
8169. 8169. So 9. Then we have 618. And now we are looking for the root between 8 and 6.
yes.
And
It's the next element after 9 in the pre-order. So this one is the root.
okay, but how did you get it from the start? Did you analyze first the pre-array or in array?
So the pre-array tells you the current subtree node.
So
okay? So
yeah.
3, right? And once we get 3, we have 2, right? 2 subnodes. One of them is the left, that's going to be immediately after it, and one of them is going to be in the middle of the array somewhere. So this is the immediate left node.
Okay.
Then the right node,
It's
we
also-
found it the way we found the other one. Yeah.
And after 9, it's also 1 gonna be the most left node. But how do
And
we
it's
know
gonna be-
it end? Like when I'm gonna reach to 1, 8, I'm gonna find 6. How do I know that 6 is? Because if I keep with this logic, I might think 6 is also the left node of 8. So there's something there, right?
Let's see it. So you have 1, which is the root of this element, right? We now we can split this, right? Let's split this and have it like this. Now we only have 1 element here. We know that this element
Okay,
is
it's
the
the end.
next child of 1.
Okay.
Right, and then we move on to the next one, and then we also have 1 element. Now we know this is the direct child of this. Then we can skip these 2. We don't need them. We already
nice.
have them.
Yes. Okay, so I
Go to
understand
the
content. The pattern is like we use pre to get the root, and then we use n to find out the left child and the right child, and we go back to pre, we skip this child because we use pre only for detecting the root, and then when I detect the root I go to n and find out where is the left child, where is the right child. That's genius. Nice.
So we can start making some sort of code. So first of all, what are we using? DFS, BFS?
We have like 2 array. By the way, who guys did not understand or like still struggling to understand? Like you have question or anything? Please open mic, talk, or write in chat. Okay, are you sure you don't have any question? I know you have a question. Come on, just say it. Don't be scared. Really? Okay, we continue, I guess. So now can we, like, before we do the brainstorm for solution, can we like kinda create the final array? Let's see how it's gonna look.
Final array.
Let's just go through this 2 array because we're gonna return array, right?
No, we're gonna return the node, the root node of the tree that we made. This is just a representation of, well, I guess the result. It would just be a representation of it.
Yeah.
But we're actually returning a node.
Yeah, but like I wanna, like, you see the output. Can we like design something like that?
Sure.
Or
I guess
it doesn't make sense.
visualize it. We can visualize it.
Wait.
Would be better.
Wait. Because we're gonna create it, right?
Yes, we're gonna create the tree. Something like this. And what they did was just go 3, 9, 20, null, null, 15, 7. That's all
Oh,
they did.
okay. So, okay. I don't know how to.
We can do a simulation of going step by step and then like making the tree on the side as we go. Okay, so we said that we know that the root is 3,
3, yeah.
right? Then we can split this array into 2 sides, right? The left side and then the right side with 3 in the middle, right? We have this, which is guaranteed to be every node on the right side of the root, and then this side, which is guaranteed to be the left side of the root. And then we can do the same operation on this, right? We find now it's gonna be 2 little things. So we find the root of this. We, I guess, shave off this. Now that we found this root, we remove it, right? And we start from here. Now our array starts from here. Now we know that the root equals 9, right? And we're gonna take these and we're gonna separate the root from them. Now we have, again, this side and this side. We move on to this one. We don't forget about it. Now, we said that the element before the root, which is 2, is gonna be the same element before the right root subtree or subtree root, right? So it's 20. Now here we know that the root is gonna be 20. We take this and then we split it, right? We go back to these. We now have the next element, which is the next root, which is 1. So root equals 1. We take 8, 1, and 6. Now we have 3 elements. We move on to this one. We know that root is gonna be before 9, so 6. We look for 6, and the next element is 5. You know the root is 5 without even looking at this. Now we know that it's 5, 4, 2. Go back to this. This is already made, right? We know that we have it is 2 elements basically. We have 15 and we have 7. We can do like another one where we know that 15 is the root and it's gonna have null on both sides. We know 7 is the root and it's gonna be null both sides. So now we can make this little, I don't know how to write. So it's a 20, right? And then on the left side, it's a 15. And on the left side, it's a 15. On the right side, it's a 20. It's a 7. Now, this is our little node in the middle of nowhere, right? We have this. Let's keep it on this side. Let's go back to this one. It is the same thing. We have 1 left node, 1 right node, 1 middle node, right? So we do basically the same thing here. Somewhere again in the middle, we have 1 as a root, and then 8 as a left, and then 6 as a right. Again, separate somewhere in our memory. We go back up. Now, we have this as a return from this operation. We have this node 1 and then 8 and 6 as children. So we put this here. We do the same thing for here, right? This 4 5 2. We do the root is 5 and then 4 and then 2. We make again our small little tree with a root of 5, a left of 4, a right of 2. Now we have these two as kids for this 9 root. Now we can put these two now together with a 9 as a root. Now I can say that I've put these two together, this mini subtree with 9 as a root, and then 1 as a left, 5 as a right, and then these are their children. Still separate from this. This is gonna return this little tree. This operation is gonna return this, and we're gonna, I guess, glue them together with this root node that is 3. So we take this here, and then this here, and then basically glued them together.
So this is like a recursion,
here.
Like a defish.
Exactly. Now we have our tree, like this. Yeah, that's our tree.
Nice. Okay, it makes sense now.
Good. Anybody else have a question?
Okay, maybe if someone have question, it also can be more clear in when we can write the code or the code. Someone is writing, maybe they have question.
Yes, in pre-order, the first element is 3. Okay.
So first we take the first number of pre.
So the root value equals 3, which is pre-0. Okay?
Someone had a question in chat if you want to.
Does that mean that you are taking every element of the pre-array as a root in each recursive call? Technically, yes. Technically, every element is a root, and even the leaves are roots at some point with null and null as children. So yes, basically yes. Every element is a root at some point. We're gonna write the code or the pseudocode soon, so I hope it makes more sense when we do that. But basically every split that we do is a recursive call. We have a pattern and like an operation that does this, and we keep calling it with either you can pass it like I can pass this array as an inorder subtree of its own, right? Or I can pass indexes to say like it starts from here and from here, then start from here and from here, and then you keep doing the same operation on every chunk of inorder like array until you have basically either singular like nodes or you have null, which means that in this case like this is empty, it doesn't have like a child. So first we look for the first element of pre, right? And then what do we do with that? We look for that in our inorder.
There's a question in chat.
Yes. The second recursive call using 9 as root. How do you know to stop at 2? As in 4, 5, 2. In the second recursive call, which is this one, how to know to stop at 2. Well, basically, if I pass this as an array, this would be the end, 2 would be the end, right? And you split it from the middle. So you always have the limiters. Either you pass the array as is, or you pass indexes to say that this is where you should start, this is where you should end. I'm not sure if that answers your question. Okay. So now with this root value, we're gonna look for it in our inorder array.
And split.
So yeah, so we can use index of, or I guess index to look for 3 in that, and it will return the index of this element inside the inorder array. And since we know that the elements, each value of inorder is going to be in preorder, we don't have to worry about any errors or anything. We know that this element appears here and vice versa. So now we have root index. Right, what do we do with this now?
Anyone have idea?
Keep this next to us.
I guess the goal was to split the array.
Exactly.
So maybe slice. Like slice from that index far left and far right, and put some left array, right array.
Okay. So left n equals n from the middle, from the beginning to index, right? Like this. And then right
From the index to from index plus 1 or
from index plus, yeah.
Okay.
Because we want to exclude this, so plus 1 to the end. Okay, now that we have this, what do we do with it?
Okay. Who guys wanna like brainstorm here? What do you think we should do? Now we split the array.
Yes, we have a left side and a right side.
Okay, if I look at the thing you did right there, it was a root equal 9. So it was like 3, and then it's equal 9, and then 8. So I guess we loop again on the pre, and we have now a new root. So this is kind of like a loop or like a recursion. So
we will use recursion for this one because I have not checked out the BFS version.
Yeah.
But for DFS, you basically want to do the same thing again, right? On this one alone, and then on this one alone, on the right one.
Yeah.
So we call
I guess
DFS.
I guess this time we're gonna send it the left in, and the other one gonna save it in right in.
Okay, so left in, and it's gonna give us the left node, right? And then right in, right, calling it on the right array is gonna give us the right nodes, basically. The root of the right subtree.
Okay, so maybe we'll call it like a root left, root right, like the variable.
Okay. Root right, root left. Okay. Now, what did we use? We used pre, right? And we want to pass pre to this function in a way that the first element is always the root. So in this case, we can just give it like a 1, like instead of 0, it's going to be 1. But in the right one, it's going to be tricky because we have to travel all the way to the middle to find 20.
Wait, can you repeat that?
In the left side, right? The next root is going to
Is
be
9.
just the current root plus 1, right? The current root index plus 1. But for the right root, we're going to have to travel all the way to somewhere in here, right? To find the root of it. The one that we did earlier where you look for 2
Wait.
and then the one next to it.
Oh, sorry, cutting you off. Wait, I
No,
forgot. Like,
go on.
why we wanna travel to there?
Because here, this is the way that we found the root value and the root index. We made it so that the first element, we look for the first element. This is what we're doing here. So I want to send pre in a way that the first element is gonna be the root of this little tree, and then the same thing for here. So let's make like an example here. I want to send pre, but I want the first element of this pre array to be the root, right?
So it's
I
gonna be
know
9.
that the next root is 9, so I can just do this pre 1 like this, and I know that when this recursion comes around and it looks for that first element, is gonna find it. It's gonna find this one. Does that make sense?
It does. And the other
In
one,
this case,
the other one is tricky, like you said, because we need to check for 2, and then so we can know it is 20. But I'm just trying to remember what's the goal from the root left, from root right. So, okay, let me go through it one more time.
okay.
So we got the pre. We select the first one root, which is 3, because that is the root. And then we were like, okay, what is the index of the root 3, but inside the in order? Then we find out it is in the index wherever. Then we split now we have 2 array. We have the second array on the left, the first array on the left, and one in the right. Now the mission is this both array and the left and the right, we need to find their root, right?
Exactly.
Now
Yes.
to get their root, we need to go back to the preorder array and find somehow the next root from the left, but to get the right root, we need to traverse until the end of all the nodes in the left side, which is tricky because, or maybe it's not tricky because
Okay, here's another-
we can just because we did split it, so we can just get the element on the far left of left and then add +1 to the index of it, and then and we know that is the start, or like +2 maybe.
Will not always work. That probably will not always work. That works for the left one because you keep going to the next one, but that will not work for the right. So there are two things. You can look for this one and go to the pre and use the index again and then go +1. Or there's one thing. I have the root here. I have a limited number of elements here. I have 1, 2, 3, 4, 5, 6, 7. I have 7 elements on the left, right? I know that we're gonna have all of those elements before we move on to the left side, right? Because I will traverse all of the elements of the left before I move on to the next node. And the root of it is going to be the first one I arrive to after finishing with the left side. I can just count how many
Oh,
3, 4, 5, 6, 7, and I have my 20.
wait,
I remove the
wait.
yeah.
What if we did use pop to remove the node that is with red? So when we reach there, the first element is gonna be always the one we're looking for.
Gonna pop everything here.
Yeah, so like in the root value pre-0, you see the pre-0 in your code? Pre-index 0. Root value equal pre-unders and what is that? The first line, pre-0.
Yeah.
We do pop 0. So every loop we pop it. So when we reach there, it's gonna be.
We're not gonna use loops. We're gonna use recursion.
It is recursion. So
It is
every.
not recursion if you're popping, because whatever you popped, you wanna leave it because you're gonna send it to somewhere else. If you pop it, you're gonna use it immediately, and then where are you gonna put it?
Okay, so let's do a simulation.
Okay.
Let so root val equal
The root is 3.
okay,
Okay.
so index 3. Okay, so how did you so you did write index 3. Why did you write 3? Maybe you write root val. Is it a root val? Now add to it pop
So here.
pop 0 or wait. No. We need to pop inside index. So just write inside the okay. Change pre-0 to pre.pop0. Pop.pop0. Okay, so now what's gonna happen is
We're gonna have
we're gonna have
this.
a tree inside root val, right? The value tree is registered inside root val. Now we have an index of tree, right? And we split it and we send DFS. This time we send just pre, like in the first argument we just write pre, and the other one also just pre. So when the left gonna keep popping on all the left side, when it's gonna reach the right side, we're gonna be popping everything. It's gonna start.
Okay. All right. That makes sense, actually. That does make sense.
We can try it.
Yes, we can try it. Can we guarantee that this pop is gonna like keep popping the same thing?
Yeah, we guarantee it's gonna keep popping the first element, and like each recursion function, it's gonna pop one pop, but it's in order. So like, it's gonna like pop 3 and then call a function and then pop 9, pop 1, 8, 6, 5, 4, 2, and in 2 it should stop because we need some condition here, right? Oh no, the condition is the left in, right? Because the array in left in is limited.
Yeah, but what do we do once we get to 2? We need a condition that checks basically if something is empty.
Yeah, if left in is empty.
Because so far we have not created any nodes. We're supposed to be creating the nodes. So once we get to 2 and it is a singular like node, we create it, we actually make it.
Okay, we can create it under index, under the line 3. We can like
Line three.
do, yeah, line 3, the empty one. So we are creating actually the root, right?
What if pre is empty? What if I am at 7 and I've already popped in? Does it still go through?
We need some base case. We still didn't design base case.
Yeah.
You're returning array, right?
Can you repeat?
From the question on LeetCode, it shows that we're returning an array.
A tree, a node tree. We are creating a tree, a node tree. Like if you see in the code on the right side, the part that it is commented, it's called like definition for a binary tree node. It's called class tree node. So we're gonna create each node. We're gonna create it with this class, and we need to connect them using the attribute left and the right. And then we're gonna return the root tree, which is all connected under it. And the representation.
This is basically their representation of the tree. We return the actual nodes, and this is what they come up with. Basically, you return this, and they make it into this, so to make it easier to, I guess, check or whatever. But you actually return the binary tree, the root of your binary tree.
That means the base case should just be if when you get to 2 or 4, it should return null then, or how do you account for writing null?
I didn't get that.
Can you repeat?
That means when you get to like the tree you drew on the right side, I think 8 is a leaf node, 6 is a leaf node, 4 is a leaf node, 2 is a leaf node.
So you're talking about second line or the root tree? Root 9 or which line?
The tree she drew at the top right.
Oh,
the
yeah,
tree.
3, 9, 20. Which part?
Yeah, the leaf node 8, 6,
Yeah.
4, 2,
Yes.
15, 7. So after when you get to 2 and the recursive call, then there's a recursive call made on 2, I guess, or on the child of 2. We should return null if there is nothing else to pop.
Yeah, because it doesn't have children. You're right. So that is got to be the base. Yeah.
How do we check if there's nothing else to pop?
So
Means,
I guess.
yeah, that is.
Yeah. Can you repeat what you said, Imak? I think I cut you off.
So that means from the way since you said we are calling the recursive call on each member of the pre-array, that means when there is no member left, that means pre.pop. I don't know if there's nothing in the list. I don't know if pre.pop is going to work.
Remove it. Yeah.
Yeah.
Well,
so
it probably would not be pre because, for example, this should return, right? But there are still many more elements in the pre. I think we should be using in since we're passing the array, right? And if this has only one element in it, then we know it has no children for us to keep moving forward with the rest of the code.
okay, so that means we're using the length of the array in.
Yes, exactly. So if len of in equals 1, then we make the node. So we have one element here. You make it and you return it. For this to So this would be the right in, or this one, right? The root right. This node is gonna get returned to become here, and I guess we return node.
Maybe we
And
designed a function definition with the arguments, so like we can see it, like dfs something. So we need we need in.
We need pre, and we need in.
Okay.
That's all we need,
okay.
right?
Yeah.
And if it's only one element, and I guess we can do this for visual effects, but it returns the node.
Okay.
Right.
I still don't get it if it is one node.
So okay. I found 5, right? I am at 5. The root value is 5. I will call the recursion function for 4 and for 2. Now when I am at, say, 4,
it's only one.
My in is gonna have only one element, which is 4. When we're here, it's gonna have 4, 5, and 2. When I split it down the middle and send only 4, I have one element here. I know that there's no point of sending more because it's null. We have only one element.
But
when we were here, if it has 2, which basically has, say, we can remove this one. This will have 2, right? It's gonna send a recursive call to 4 and to a null. So I guess we need another guard here to check if len is
null,
of n is empty, so we can return null. And then in this case, the root left is going to be a node that gets returned from here, and the right node, quote unquote, is going to be null. So it's going to assign null to the right. I guess we should finish this first before we start talking. So here in this case, we're going to make a node. And the val is going to be root val, right? The left node is going to be root left.
And the right node gonna be root, right? And then we return it.
Exactly. And we return our node. Okay? So if we have only one element, singular element, then we make that node with that value, right? Which is going to be the only value in, right? And the left or right, I think they have a non-default. So we just put the value, and then left and right are going to be null. And whatever that returns to its root, then again gets added as a left and as a right, and then that gets returned to 9, and again 8 and 6 are going to get returned to 1. 1 is going to return this root to 9. 9 is going to have left as 1, right as 5, and it's going to return that to 3, etc. Until at the end you're going to have 3 with the rest of the tree. And you return.
Nice.
Okay.
Perfect.
Any questions before we code this?
Please don't be shy. You have a question?
Okay. I guess we can.
Oh wait, I have a question. Scroll up. Right?
Yeah.
The length one. We make the node. Wait, isn't we did... Wait. Wait, go back... Sorry. Go back to Excalibur. So, if the length is 1, we make the node and we return it. But
Yeah.
aren't we make the node in the previous call? Like before we call this? For example, if I am on the node 4, or like if I am in the node 5, if you put, okay, and now I'm gonna create, it's gonna check the length, it's gonna say length is 1, okay, so I'm not gonna enter here.
Actually, it's gonna be length of 2.
Yeah.
It's gonna have 5 and...
Yeah, it's like it's gonna say I'm not length of 1, so it's not gonna enter here. When it's gonna call on 4, okay, like put something on 4. So like when it's gonna call on 4, it's gonna say, oh, length is 1. Let me make a node and return it.
to 5. Yeah. Now 5 is gonna take this node and this null node or null, and then it's gonna make it its own node with these two as children.
Okay,
So
I see.
any leaf gets caught in this, and any other node that has one or more children can make it to here.
If we remove that check of length 1, I think it's still gonna work.
Okay, it's gonna move to root, it's gonna pop it, it's gonna get the index. These two are gonna be empty. Yeah, I guess it could. We can remove that and see if it works.
It's just gonna
It's
have a null input left and right. Then it's gonna connect them at the end.
I guess we can remove it. Then let's go to code. So if len in, so this is pre, this is in. Oh, n is gonna be an issue. Okay, so if len in order equals 0, then it's gonna return none. And then our root val is gonna be preorder and pop 0. Our root index is gonna be in order. Index of root val. The left in order is gonna be in order from the beginning to the root index excluded, and the right in order will be in order from the root index +1 to the end. Now root left is gonna call the recursive function with the current preorder and the left in, and root right is gonna call with the same preorder but popped with the right in, and then we make the node. So node equal node, the value, this val is gonna be the root, so the root val. Right? The left is gonna be this root left, and then right is gonna be this root right.
Wait, is it a node or tree node?
Where's tree node?
The class. class name.
Oh yeah, you're right. Try node. Okay.
Now we create it. Now we return it.
And we return. Exactly. Okay. See if this works.
Ooh.
Oh. We need to call the function. So return DFS with our pre-order and in-order.
Ooh. Ooh. What was that? Or not?
To make difference.
Ooh.
Oh,
First try.
hey,
Nice. First try. First try. Good job, guys.
probably will not pass some time limit.
Oh, it did.
Oh, it did.
Wow.
It did.
I'm surprised.
Okay. So you can see that there are two separate
Oh yeah. Why? Two
time
methods.
groups. Yeah. Not two methods, but a trick that makes it a split, I guess, some seconds or a split seconds faster.
Okay.
So, this index is quite expensive. It goes through all of it looking for this value. I have seen people making actually a dictionary. So vals equals guess key
Like
val
memorization or something?
exactly. So they go through it and they keep track
Oh
of
my
indexes
god.
and values. And going through this, finding an element in a dictionary is easier than to find it in an array. Use an index. So basically, a hash map of keys and values. So I guess key as index. We can do index here. Index value for index val in enumerate of what is it? Preorder. Right? And we can, instead of doing this, we can just go to vals and our root value. And I think I should be flipping these. So the value becomes the key that I'm looking at, and the index becomes the value. So index. So now when I look for this value in my values hash map, I can easily find its corresponding index. See if it works. If it's even faster. Okay, pop from an empty. Oh, what happened?
Why pre-order it's empty? Oh, the first time. The first time it's gonna be empty. So
Okay.
we did not. Okay. No.
It passed last time. It passed last time. Why did this make it not pass? I'll keep this. And then let's go back to the way it was. So this passed.
Because it's not empty.
No, but we didn't change anything about this. We changed
We
this.
changed. We pop it. So
No, we didn't touch this. In our new version, it did not touch this line. We only changed the way we look through this.
okay, I think I missed that.
Oh,
Okay.
wait. Oh, no. Okay, I think I did something wrong here in the way I look for. It's gonna be, this should be in order, not pre-order. Oh God, this should be in order because we're looking in for the index in order, not pre-order.
But why it give error at first?
So I am assuming that since
Oh, it's remove. Maybe the enumerate it's remove elements from the in order.
no, it does not. It does not. But maybe it keeps it going. Maybe in a. Actually, I have no idea why.
I think it's remove them. Can we check?
It does not. It does not. But it gives us the wrong index, and we're using that index for the splitting. So I guess it keeps it running beyond what it should run for. But I know for sure enumerate does not remove elements.
Okay. Nice.
Oh.
How much is improved?
We have not tested it. Oh my god.
Pop from empty list. Which line is this? Pop. It
This
said
one.
pop. Can we print pop pre-order?
Pre-order? Okay.
We didn't add a check for pre-order.
Yes, but it works for some reason. Yeah, it popped.
Yeah, but it's empty. But if a pre-order is empty, we should not pop if it is empty, right?
I have a feeling that this might not be correct. Let me. Okay, so print root val and root index.
I think you should check line 12, where we say if length of in order equals to 0. Are we also supposed to check where pre-order is equals to 0 too? And then return.
Oh, we are using the in order still. We're not using the hash map.
Where?
Wait, can you repeat your thoughts? I think Sean also who talk.
Okay, I'm saying that in line 12, where we have if length in order equals to 0, are we not supposed to also check if length of the pre-order is also equals to 0 and then return none? So we'll know that we have gotten to the ending of the pre-order.
This makes sense, I think.
I think I know exactly where the issue is. This vals checks for the whole in order. Checks for the whole in order array. But here we are splitting it. So whatever value this will give us will not be accurate in reference to our current in order array. Because this takes like a snapshot of the in order when it's complete, when it's the whole thing. Right? So this would actually work with indexes if we were to exchange indexes instead of splitting the in order. If we were to pass, for example, start of in order, end of in order, right? And in order would still be complete. That would work, right? It would give us the index in the middle of the in order array. But in this case, since, for example, it would be, this is our in order array, for example, and it gives us, for example, 3, our array starts with this, so 0, 1, 2, and it's going to give us issues that I guess at the end leads to this, to the pre-order array being popped, I guess, too many times or way more than it should. I guess if I print the in order, we would have, like, I guess, empty, a lot of empty lists, I'm just assuming. So yeah, the inorder is empty, but it's still, I guess, kept popping. Maybe? I'm actually not sure, but I guess the issue is that this is not accurate with the inorder array that we have at each iteration, at each recursive call.
Yeah, it doesn't work for this solution the way we choose the split.
Exactly. So, I mean, if we have time, we can test it with the indexes. If not, then...
Yeah, we have time. We can try it.
So in this case, we would add a start and an end. And then instead of this, we would be equal. So we're starting with root index, right? So for, 0. So it's gonna be the left and starts from 0, ends at root index, so it still starts at 0. And then the end would be starting from root index plus 1. But again, that is still reliant on this being we can do that, even though I know it's not correct, but we can just okay. So start and then no, wait, this doesn't make sense. Okay, so the start for this one would be the same as the start that we have. The end for this one would be root index, and then the start for the right would be root index plus 1. I'm not sure if I'm making any sense, but
I'm trying.
and the end would be the normal end. I'm having doubts with this one. This does not make much sense in my brain, but it probably... Okay. And then here we give a start and end, and then here it starts from 0, and it ends at len in order. Plus 1? No, just minus 1. Right? Oh, that works.
Okay, I'm still trying to put idea in my mind. Not yet.
Let's just check if it works before.
Okay. Then explain it.
We don't in order. I mean, I guess it's inside here. We don't technically need to pass anything, right?
Yeah, if it is,
We're inside this one.
we don't need to pass.
Neither in order nor preorder.
Yeah, we are inside this.
That could have actually slowed the first version that we passed. Let's try. Pop from empty. I have no idea now.
Can we wait
I
about this?
have no idea.
Can you repeat, Emax?
Can we whiteboard this on Excalibur?
Oh, okay. Let's take these two. Okay. Now, in this new version that we made, we are still popping from pre, so this is still the same, But for here, instead of splitting the array manually, like we're doing here, instead of doing the recursive call with this and then doing another recursive call with this, we're actually keeping the same array. We're just telling it with pointers, telling it, hey, I guess this is where you start and this is where you finish, and you don't go beyond this. And then you tell to the right one, you start from this one, which is root index plus one, and you end at the end that I've given you. So you start at the start of the array. So if I pass start to this one, it's gonna stay with the same start, but it's gonna end with the one before the root index. So in this case, from start and root index, I guess -1, should be -1. But we tell it, hey, go to start from the start, end at the root index -1, and then start again from root index +1 and end at the end of the array that I've given you. So this is what we do in here. We start from the start that we've given. We end at root index -1, the one before it, and then the right call would be from the root index +1 till the end. Still doesn't work, but pop from empty array. So 7. So in this case, it should stop, right? It should go here, but since we already popped it here, it shouldn't be able to call anything else. Should maybe put a guard here, I guess. So, this one should be maybe comparing start and end. If start equal end, since Inorder is still one array. Nope. Start is bigger than equal. That doesn't make sense. Okay, at least we're not getting errors.
Can we put the whole code like in Excel? Let's see how it works. Can go like line by line. Detect back. Maybe shrink it or like zoom out. Okay. Oops.
Of course.
That's it.
Okay.
That's the code.
Okay. So it creates the array, the hash map, and then it calls.
Can you do so like this hash map if you wanna imagine it in my head? So it have keys as what?
Okay, it's gonna have, for example, in here, it's gonna have the value 3 with the key 3 with the value 0, key 9 with the value 1. But this is for the Inorder, but it's gonna do it for that what I did was Preorder. It's gonna do it for the Inorder. It's gonna go 9 and then 0 and then 3 and then 1, 15 and then 2.
Okay. And the goal from this was to
avoid using index.
Yeah.
To easily go to this and find the root. We find it here.
And then we enter. We did if len. Okay, maybe we. What was the condition there? The
here to check if that the start and the end are in the same node. Right? So basically, if we have no nodes, like the same condition that we had where Inorder is empty, I guess this replicates it. Since the start and the end of our current array would overlap, or start would be bigger than end.
Can you create two pointer like with color for start and end? Because I can't imagine them.
Okay, sure. So we have this, right? At the very first call, right? 0 would be the first pointer, and then len of Inorder -1 would be the last pointer, right? At the first call, I would give it the same 0 for the left. Now for the left, the start would be the same, which is 0. At the end would be root index -1. It would be this again, right? Oh, wait. This should be bigger than, because if this should still return something, it should not return none. So this should be just bigger than, because we still want it to go through the rest of it if we still have just one. Okay? Then on the right side, it's gonna have root index +1. Let's give it another color. It's gonna have this one +1, and then the end is gonna still be the same, right? On the next recursive call on this side, this is gonna be the root, is gonna send the same start, and the end would be root index -1, which is again the same one, and the next one again, root index +1 with the same end. Does that make sense? So we keep juggling these start and end to show us where we are in the long array and the big array, without actually changing anything about the array.
Okay.
Still need to make it work though.
But let's go through. Ooh, that was the problem. Nice. Okay, clear.
Hopefully this should be faster. Did I do? Okay. So. Did I do? Okay.
Oh my god, what? 98. Wow. Wow, that's amazing.
That is.
Wow. Nice one. Don't submit again. I'm curious. Submit, please. Maybe it's gonna become 100.
No. Oh no. Okay.
I missed the explanation.
Nice.
Could you go over the code again?
Can you repeat it, Max?
Yeah, I missed the explanation. Network. Could you please go over the code and what was the issue?
Yes, I can. Okay. Let me remove all this. And okay. The bigger array would have made like a better yeah. Let's use this one. So the first thing we do is to have a hash map with the value as key and the index as value for the inorder to make it easier to find whatever root we have inside the inorder array. That is the first step. And then we call the DFS function with 2 pointers, right? We have a left pointer and then we have a right pointer. Maybe I can make them thicker. Left pointer and then the right pointer. Okay, now I have the left pointer at the very start of the array, so it's a 0, and then another right pointer, the end pointer at the end of the array. Right, I go through my DFS. Start is very far from end, we skip this one. And then we now look for the root of our tree. The root we said is guaranteed to be at the start of our pre-order array, right? So we take the first element and we pop it. So we basically remove it from the array, the pre-array, right? And then now that we have the root of 3, now that we have a root of 3, right? We look for this 3 that we have inside of here. Now the hash map inside of the inorder array. Now the hash map made it easier to find that, hey, we have 3 here. Now this is my index, basically, of the, not the index of the root of this array. This whole array is here. Anything on the left of it, oh God, anything on the left of it is on the left of this node. Anything on the right of it is on the right of, is right children and left children, right? Now, this root is gonna get passed as a, almost like an anchor, right? I know that my root is here, and I want to check or make nodes for the left side. So this is gonna be my delimiter. When I pass, oh God, when I pass, like when I find my root as 3, I am gonna pass the end of this new array as the root -1, because I know this is my root. Anything on the left of it is left nodes. Now, when I want to make my left subtree, this is the delimiter. Same thing for the right. I am gonna have 3 as my root, and it's anything on the right side of it is a right subtree. All right, so if we see it here, anything on the left starting like 9, 1, 8, 6, 5, 4 are left subtree. And the right subtree starts with 20, 15, 7 is what we have here. 15, 27, and then this whole array. Now, if I focus on this one, right? If I focus on this one, I can find my, again, I'm gonna go through it, blah, blah, blah. I'm gonna have the root value is gonna be the first element of my pre-order tree, right? So now I know that the new root is 9, right? And I have my new delimiter, right? I know that anything on the left side is a left subtree, anything on the right side is a right subtree, keeping this as an end. We don't even mention the rest of it, right? So if I copy this, right, I have the start of the right being the root +1 and the end being the end that we already had. And the same here. We start with the start that we already had and we end at root -1. And we keep going until, again, we go through it again, and then still start is smaller than end, blah, 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 until what do we have? We have root is 8. We skip the 1 since it's going to have, again, 1 is going to give me like a pointer at 6 and then a pointer at 8. And it's gonna again call another recursive call since start is bigger, is equals to end. In this case, it's gonna send the pointer as 8. The start is 8, the end is 8, and here again the start is 6, the end is 6. It's gonna skip this one since they're equal, and it's gonna call a recursive call on just 8, with the left being null and the right being null. Right, so now when it's gonna call it again, start is gonna be bigger than end, since we are going with 8 minus 1 and then 8 plus 1. So in this case it's gonna be minus 1, in this case it's gonna be 1, the end is gonna be minus 1, start is gonna be 1, and it's gonna get caught here, returns none. So this one returns none, this one, the right side of 8 is gonna return none. The left side of 8 is gonna return none. So we're gonna make our node with the value of the root that is 8, left being none, right being none, and this node is gonna get passed to 1. 1 is gonna again call the recursive call on the right side, is gonna do the same thing. 6 left none, 6 right is none, is gonna return the node 6 with the value 6, left none, right none, and then now 1 has 2 nodes. Root left is a node, root right is a node, is gonna glue them together, is gonna make a new node with the value of 1, and the left being the node that we returned here with the value of 1. The right is gonna be 6, the node with the value of 6, and yeah, this new node now is gonna get passed to 9. The previous root is gonna do the same thing. It has a node on the left, it has a node on the right, it's gonna make a new node, is gonna, with the value of the root that we had, and left being left, right being right, and it's again is gonna send it to here. Hope that made sense.
I think it's quick sort. Some points the start is greater than the end.
Can you repeat? I didn't catch that.
Yeah, I'm saying the condition is like the condition of quick sort algorithm. At some point, the start is going to be bigger than the end.
Yes. When we get to the individual node.
Yeah, that makes sense. Thanks.
Okay. Nice.
Any more questions?
Anyone have any question? I think not. If that was it, thank you, Sabah. Thank you so much for hosting this session. It was amazing. That was it for tonight. And tomorrow, see you guys. And if someone wanna host any LeetCode tomorrow, just hit me up, and yeah, we set up something same hour, same time. Bye. Have a good night. See you.